Come on my dears, kindly read this statement of MCQ number 17. Have you read it? Look, we have 2 point charges, capital Q and 9 into capital Q, separated by 4 meter distance. Okay? What we are asked to find out? We are asked to find out total electric potential at that point where resultant electric field produced by these 2 charges is 0. Correct? Look, along the line segment joining these 2 charges, the point where resultant electric field becomes 0 is called a null point, and I told you earlier the position of null point is closer to smaller charge away from bigger charge. Compared to this is smaller. So this null point position is closer to this smaller charge and away from bigger charge. Correct? Suppose that point P is at distance r1 from first charge and at distance r2 from second charge. What is the total distance? Total distance is 4 meter, out of which this much is r1. So remaining distance would be 4 minus r1. 4 minus r1. Correct? Fine. Now why electric field here is 0? The reason is that, look, you know this is positive charge, and due to positive charge the direction of electric field will be pointing away from it. So away from this charge is this direction, and it is electric field produced by first charge, so I am showing by symbol E1. Similarly, this is also positive charge, and electric field produced by this charge is also away from it at this very point, away from this, so the direction will be like this, and it is due to second charge, so I am showing it by symbol E2. Correct? Now tell me, if these 2 electric fields which are in vertically opposite directions and they are collinear, if they have equal magnitudes, then resultant electric field at this very point would be 0. Correct? So I have written here EP equals to 0. Now tell me, if resultant electric field at point P has to be 0, then these 2 oppositely directed electric fields must have equal magnitudes. That is, E1 must be equal to E2. Correct? What is the formula for magnitude of electric field due to a point charge? Have you remembered? K into charge upon distance square. Correct? So K into first charge is Q1 upon distance square. Come on. Square of the distance of point P from first charge, that is R1 square. Similarly, E2 will be, come on, K into Q2 upon R2 square. Correct? K into charge upon distance square. And now KK will cancel. Correct? Q1 is capital Q. Q1 is capital Q. Q2 is 9 into capital Q. Q2 is 9 into capital Q. R1 square as it is, but R2 is 4 minus R1. R2 is 4 minus R1 and it's a square. Now simplify. Q and Q will cancel, and now take square root. Square root of 1 upon R1 square will be 1 upon R1. Square root of 9 is 3. Square root of this is 4 minus R1. Now simplify and find out value of R1. It comes out to be 1 meter. 1 meter. And now what is R2? It is 4 minus R1. 4 minus R1, R1 is 1 meter, 4 minus 1, that is 3 meter. So we have found out R1 and R2. And now what we are asked to find out? Total electric potential at this very point. At point P, so I am giving symbol Vp. Correct? I told you earlier, as many charges, that many values of electric potential. So if we have 2 charges, then we will have 2 values of electric potential, and then we should make their algebraic addition in order to get total electric potential. Correct? Now potential due to a point charge, come on, by formula, K into charge upon distance. K into first charge is Q1 upon distance of point P from first charge is R1 plus similarly potential due to second charge would be K into second charge Q2 upon distance of point P from second charge which is R2. Now K and K should be taken common inside the bracket. Come on, Q1 is capital Q. Q1 is capital Q. R1 is 1 meter plus, come on, Q2 is 9 into capital Q, 9 into capital Q, and R2 is 3 meter, correct? Put the values, simplify, 3 3s are 9, so here it is 3Q plus Q, that is 4Q into small k, that is 4 into small k into capital Q. This will be the total electric potential at point P which we require, okay? So this is our final answer, got it? Fine. Read now statement of MCQ number 18. Have you read it? Look. Potential difference across charged capacitor is charge upon capacitance. Charge upon capacitance. V equals to Q by C by formula. Okay. Now this charge they have given 50 microcoulomb. 50 microcoulomb. You please convert it into coulomb. Multiply by 10 raised to minus 6. What about capacitance? They have given 600 microfarad. Convert it into farad, multiply by 10 raised to minus 6. Okay, come on, simplify. You will get V equals to 5 upon 60, that many volt. But here they have given that this charge on the capacitor increases at the rate of 50 microcoulomb per second. So voltage also will increase by this many volt per second. Correct? Here I am writing now voltage in volt. And oppositely I am writing time in second. Voltage increases by this much amount, 5 upon 60 volt in 1 second. Time is 1 second, correct? Per every second, charge is increasing by 50 microcoulomb per second, and per every second this voltage increases by 5 upon 60 volt. Okay? So this much voltage would increase in 1 second. Then we have to find out time for voltage to become 10 volt. Come on, for 10 volt voltage, what is the time for waiting? Come on, this into this upon this. We have to wait for how much total time? This into this upon this. 10 into 1, that is 10, upon 5 upon 60. Now denominator will become numerator. 60 into 10, that is 600, upon 5, that is 120 second. Correct? Leave proper gap, put small s and don't put any full stop. Got it? Read now statement for MCQ number 19. Read it? Look. What is the magnitude of electric field on the surface of a charged sphere by formula K into charge upon radius square. K into charge upon radius square. Correct? Can you rewrite this term as 1 upon R into KQ upon R? 1 upon R into KQ upon R. Correct? R into R will be R square. Simple. Now what is KQ upon R? K into charge upon radius will give you, come on, electric potential on the surface of a charged sphere shown by symbol capital V. So this can be replaced by capital V upon R. V upon R. Correct? Now earlier in one such a similar question I had explained to you, if you have two charged spheres with different radii and if you connect them by some metallic wire, what will happen? Flow of electrons will start from a surface of lower potential to a surface of higher potential, correct? But how long that electrons will flow? Come on, how long the flow of electrons will continue? Till the potentials on the surfaces of both the spheres would become equal, correct? So once the flow of electrons has been stopped, you must understand that because it is because of potentials on the surfaces of both the spheres must have become equal. That equal potential difference I am taking capital V. So right now for both the spheres, this capital V is same and constant right now. Because V is constant, what is the relationship between E and R? Relationship between E and R would be E proportional to 1 upon R. E proportional to 1 upon R. So this is inverse proportionality. Inverse proportionality, correct? And in case of inverse proportionality, don't you know simply 1 to 2 1, 1 to 2 1. If you take the ratio of E1 to E2, you will get it equal to R2 to R1, correct? 1 to 2 1, 1 to 2 1. E1 upon E2 will be equal to R2 upon R1, correct? Fine. Kindly read now statement of MCQ number 20. Read it? Look. We have charged plates of a capacitor. Suppose this is positively charged plate and this one is negatively charged plate. The perpendicular separation between these two parallel plates is given to us 5x. 5x. Now what we do? We just introduce one dielectric slab having dielectric constant equal to 3, having thickness equal to x, such that its one of the faces just touches this one of the charged plates of a capacitor. Suppose these two are in contact, okay, fine. I mean to say this much region is now replaced by dielectric medium having thickness x. What was the total separation? 5x. Out of 5x, if you subtract x, the remaining will be 4x. So in this much region, there is a vacuum. There is a vacuum. Now, electric field is always from positively charged plate to negatively charged plate of a capacitor. So direction of electric field I am showing this way. Look here. Correct? From positively charged plate to negatively charged plate this way. Fine. But so far magnitude of electric field is concerned, it will depend on the type of medium in that region. Here we have vacuum or free space where electric field as having magnitude E0. Electric field is having magnitude E0. Now we have studied in theoretical part, if you have dielectric medium, then inside the dielectric medium the resultant electric field is kth part of electric field in the free space. In the free space or vacuum, if electric field is E0, then in this dielectric medium electric field will be E0 upon capital K, where capital K is dielectric constant of this dielectric medium, correct? Mind well, so far direction of electric field is concerned, both these electric fields have same direction from positive charge plate to negative charge plate. At present it is toward the right hand side, got it? But magnitudes are different. Here electric field has magnitude E0 and here it is E0 upon K. Now let us do one thing. Let us start moving from this negatively charged plate towards positively charged plate this way, that is in a direction opposite to electric field. Opposite to electric field, okay? When I start my journey from this negatively charged plate, the electric potential what I have here is suppose V negative, V negative. Electric potential at the position of negatively charged plate, I just assume V negative, okay? And then after I start moving this way, look here, that is opposite to electric field. You must have remembered, if you move opposite to electric field, then electric potential will increase. And by how much amount? That formula also you please remember. You must have remembered, V equals to E into D. E into D means inverse magnitude of electric field multiplied by perpendicular distance. Magnitude of electric field multiplied by perpendicular distance. When you move from here to here, What is the magnitude of electric field? It is E0. So I am writing here E0. Correct? Multiplied by perpendicular distance. Come on. It is this much, which is 4x. So I just multiply by 4x. And that much is the increase in the potential. So I am writing plus. Increasing then plus. Okay? Now you have come over here. Now move from here to here. Here to here. Again, what is the magnitude of electric field? E0 upon capital K. E0 upon capital K. Multiplied by thickness or perpendicular distance between these two faces, it is x. So I just multiply by x. And that much will be increase in electric potential. So I am writing plus sign. Okay. And now I have come over here. Here means what? Here means where? I have come at the positive charge plate. At the position of positive charge plate, the potential is suppose V positive. V positive. Correct? And now what we require? We require to find out electric potential difference between the charged plates of a capacitor. Normally the difference we find this way, higher minus lower, higher minus lower. So this is higher and this is lower, just transfer this. So V positive minus V negative, that is what we require. Come on, when you transfer this over here, these two terms are left. In that you can just write K equal to 3. Put here K equal to 3, correct? Then 3 will be taken in LCM. 3 will be multiplied here. 3 4s are 12 E0x plus E0x. 12 E0x plus E0x, altogether it is 13 E0x upon 3. This much will be potential difference between charged plates of a capacitor in this case. Okay, fine. Kindly read now statement of number 21. Have you read it? Look, we have an arrangement in which there are 4 identical metallic plates which are kept parallel to each other. Not only that, the perpendicular distance between each 2 consecutive plates is same. Now, if you have capacitance between these 2 plates, then it is given by formula C equals to epsilon 0 A upon D, where capital A is area of one plate and D is the perpendicular distance between 2 consecutive plates. Simple? Fine. Now, out of this arrangement, what is the equivalent capacitance will we have between points A and B? That is what we have to find out. Now, directly from this arrangement, you cannot judge how many capacitors are connected in which manner, that you cannot judge. Better you should think of some equivalent arrangement. That is what I have drawn over here. This arrangement of these capacitors is quite equivalent to this arrangement. Now you may ask how. I am showing you. Plate numbers I have given, and same plate numbers with the same color I have shown here also. Plate number 1 is shown with the pink color here, here also with the pink color. Plate number 2 with green color, correct? Plate number 3 with blue color. Plate number 4 with yellow color, correct? Now I am showing you how this is equivalent to this. Remember, the plates which are at the end points means there is no plate above this plate, there is no plate below this plate, correct? So these are the plates situated at the 2 ends. Those plates numbers will come in this equivalent arrangement only one time. You can see plate number 1, that number 1 comes here only one time. Plate number 4, that also number comes only one time, okay? But so far the intermediate plates are concerned, their upper and lower, both the faces we have to consider. So the number of intermediate plates will come twice. Look, plate number 2 is also coming twice and plate number 3 is also coming twice. Now I am showing you how this is equivalent to this. Look, what is opposite to plate number 1? Opposite to plate number 1 is upper face of plate number 2. Opposite to plate number 1 is upper face of plate number 2. What is opposite to lower face of plate number 2? It is upper face of plate number 3. opposite to lower face of plate number 2 is the upper face of plate number 3. What is opposite to lower face of plate number 3? It is plate number 4. Opposite to lower face of plate number 3 is plate number 4. Correct? One more thing. At point A, how many plates are connected? Plate number 1 is connected with point A and both the faces of plate number 3. Just check it here. At point A, plate number 1 is connected and upper and lower both the faces of plate number 3 are also connected. At point B, what is connected here? Plate number 2, upper and lower faces of plate number 2 and plate number 4 are connected at point B. Here also you can verify. Here at point B, plate number 4 is connected and upper and lower faces of plate number 2 are also connected at same point B. Correct? So in all respects, this arrangement is quite equivalent to this arrangement. And so whether you find out equivalent capacitance between points A and B here or you may find out here, it will make no difference because both the networks are equivalent. Correct? But here we cannot judge how is the arrangement. But here we can judge the type of connection very perfectly. You can see here all these 3 capacitors are connected in parallel between points A and B. And now, don't you know the law of parallel connection of capacitors? What is that law in words? Equivalent capacitance will be equal to simply summation of individual capacitances. What is the equivalent capacitance between points A and B? Let it be CAB, correct? It should be equal to summation of individual capacitances. Here also C, here also C, here also C. And summation of all these 3 capacitances means C plus C plus C, that is 3 into C. What is C? I told you earlier, C is epsilon 0 A upon D. C is epsilon 0 A upon D. Okay? So at present, equivalent capacitance between points A and B has come out to be 3 epsilon 0 A upon D. Correct? Fine. Just for the sake that you will understand very easily, I have not changed the color of the plate. You can see here and here. At both the places, the color of plate number 1 is shown with the pink color. Color of plate number 2 is green. Color of plate number 3 is blue. And color of plate number 4 is yellow. Okay? Fine. Come on, my dears. Now we begin with a new section. Section D for short questions. In the list of the short questions given in the textbook, question number 14 and 15. They are worth solving. I would like to solve those questions, correct? Look, in this question number 14, they have given such a network of 3 capacitors and we are asked to find out equivalent capacitance between points A and B, correct? If you want to understand very nicely, better you connect battery between these 2 points where we have to find out equivalent capacitors, okay? Now, once you connect battery in this manner, what will happen I am showing you. This and this plate, they are connected to this battery, but this plate is connected to positive terminal and this plate is connected to negative terminal, correct? First of all, the electrons from this plate are attracted towards this positive terminal of the battery. So this plate after losing electrons will become positive. So I have written here plus sign, okay? Those electrons after entering into the battery will receive energy and ultimately they are deposited here on this plate. Will make that plate negatively charged, correct? Once this plate becomes negatively charged, what will it do? It will repel the electrons from the opposite plate and so opposite plate loses electrons and so it also becomes now positively charged, correct? It becomes now positively charged after losing electrons. But now those electrons will come here Then after they are offered two branches, two paths. Which two paths? One is this path, another is this path. But if electrons try to flow here, because of this gap, they are offered infinite resistance. They are offered infinite resistance. But instead of that, if they flow here in this branch, and because it is metallic wire, it has almost zero resistance, And so if electrons are provided a path of almost zero resistance, then we say that circuit is being shorted. So electrons are now short circuited. The flow of electrons is now short circuited, and so electrons will prefer to flow through that path which has almost zero resistance. So all the electrons which are coming here, they do not flow this way, they flow this way. Look here, this way. Similarly, after coming to this junction, electrons do not flow in this branch. Because of the gap here, they are offered infinite resistance. Okay? They do not flow in that branch, and then those electrons which are coming here will continuously flow this way. It will make this plate negatively charged. So in this process, what happens? That these two capacitors are getting charged up, but there is no charge deposited on either plate of this capacitor. Because there is no charge on both the plates of this capacitor, you can say that capacitor, though it is physically present, but from physics point of view, it is as good as absent, because it has no charge. Any capacitor in any network which is not getting charged up, you may simply discard, you may simply remove. It makes no effect on the working of the circuit. Okay, fine. So if you just discard this capacitor, if you try to remove this capacitor, then tell me, once you remove this, then this capacitor and this capacitor, they are connected one after another in a queue, that is nothing but series connection. And in case of series connection of two capacitors, what was the formula of equivalent capacitance? I told you to remember in words: multiplication upon addition. That's why I am writing here, C into C upon C plus C, multiplication upon addition. That will give you equivalent capacitance between points A and B. That's why I am putting the symbol CAB, correct? Now C into C, that is C square, C plus C, that is 2C. 1 C is getting cancelled, so left is C by 2. So what is equivalent capacitance in this case? Come on, C by 2. That is your final answer. Okay. Remember, short circuit means a path of zero resistance. If flow of electrons is short circuited, meaning thereby flow of electrons is provided a path of almost zero resistance. Okay, that is called short circuit. Fine. Now read this statement for number 15. Read it? Look. In question number 15, the arrangement of capacitors they have given like this, where we are asked to find out equivalent capacitance between points A and B. As we had done earlier, here also we connect battery across those 2 points across which we want equivalent capacitance, correct? So that battery is this. Come on. Look, here this plate and this plate are connected to positive terminal of the battery, and so electrons from these two plates are attracted towards this positive terminal of the battery, and so these two plates will lose the electrons, and that is why after losing negative charge they become positive, correct? Those electrons will gain the energy from battery, and then after they will come here. Half of the electrons will flow this way, remaining half of the electrons will flow this way. But after coming to this and this junction, electrons neither flow from this point to this point, nor they flow from this point to this point, because if at all they try to flow in this branch, because of this gap, they are offered infinite resistance, where they will not flow, correct, because of infinite resistance. So, electrons whichever are coming here will flow this way, will make this plate negatively charged up, and the electrons which are coming here will flow this way, they are deposited here, will make this plate negatively charged up. Again, in this arrangement also, this capacitor is not getting charged up. I told you earlier, in any network, if any capacitor is not getting charged up, you may simply remove it, okay, and though you remove it, it does not affect the working of the network, okay. So, you can discard this. Once you discard this, then between points A and B, you will find these two capacitors connected in parallel. Here it was series connection, one after another, and here parallel connection. Why parallel connection here? I told you, if the polarity of charge on interconnected plates is same, then it must be parallel connection of capacitors. Here these two plates are connected at point A, these two plates are connected at point B, correct. What is the polarity of charge here? Positive, here also positive. So, if interconnected plates have same polarity of the charge, it must be parallel connection. So, this is parallel connection, fine. Now, in case of parallel connection of capacitors, what is the law? Come on, mathematically, you can say equivalent capacitance will be equal to summation of individual capacitances. Here also capacitance is C, here also C. So, simply make their addition, C plus C, that is 2C, okay. So, equivalent capacitance in this case between points A and B is 2C, got it? Fine. Come on, my dears. Now, if you feel interested in the subject, I would like to make 2 points very clear. Try to understand these 2 extra questions we are going to see just now. One thing I would like to tell you very frankly, so far derivation of formula of electric potential due to a point charge is concerned, and so far definition of electric potential is concerned, I tell you, we all the teachers, the students, they all are in puzzle. Really we are confused regarding plus and minus sign. Now, what is the way out? Why this problem has occurred? I would like to tell you the reason for that. Earlier in 11th standard, while defining gravitational potential, we had no problem, because gravitational field is of only one type. It is always attractive type, correct? Fine. And the source of producing gravitational field is mass, which is always positive. But here we are talking about electric field. What is the source of electric field? Charge. But charge is of 2 types, positive as well as negative. That is why, though you are having 2 polarities of electric charge and you are trying to give single definition of electric potential, then it creates a problem. You must define electric potential for 2 different types of electric field, one repulsive and one attractive, differently. Then you can use those 2 different definitions while deriving the formula of electric potential in both the cases separately and differently, correct? Then it will have no problem. But what is the problem in majority of the textbook, in majority of the reference book? They have simply not taken this point into consideration, that there are 2 polarities of electric charge and we are trying to define electric potential by a single definition. Now that would create a problem. So what we do now? We just adopt 2 different definitions for electric potential, one for repulsive electric field, another for attractive electric field, correct? Fine. My dears, one more point. Here actually we are looking for electric potential, correct? And very basically speaking, what is electric potential? In very short, it is electrical energy, that is electrostatic potential energy per unit charge, correct? So, what we should do? We should find out the electrostatic potential energy stored in a given electric field at a given point, and that energy if we find per unit positive charge, then it will give you electric potential, correct? Fine. Now, electrostatic potential energy is possessed by electric field because it has some capacity of doing work. So, what we do in these two theories which I am going to show you, we will allow electric field to do the work, correct? So, we will not bother about work done by external force. We will find out the work done by electric field because it has capacity of doing that work, and how much work it can do on a unit positive charge while bringing it from infinity to a given point or while pushing it from a given point to infinity. That is what we will find out, okay? And depending upon that, we will get the potential value at a given point. Got it? This is our basic idea. Look now. Let us see first of all electric potential of repulsive electric field at a given point. Consider this positive stationary point charge, say q dash equals to q, correct? Because it produces its own electric field, it is a source of electric field, we call it source charge. But that source charge right now we have taken positive. For a positive point charge, don't you know, its electric field lines are radially outward. Radially outward. Fine. You just do one thing. Consider a test charge, say Q0, shown by symbol of dot at point A. So, point A is the initial position. Okay? Fine. Now, the distance of initial position, that is point A, from this source charge I have taken equal to R. Correct? Now, just release this test charge from here. Just release it. You know, test charge is always positive. Source charge is also positive. Test charge is also positive. This will repel this charge. So, it will move this way. Correct? How long? Till electric force remains exerted. Okay? Electric force will remain exerted till infinite distance. Correct? Because F is proportional to 1 upon R square. Unless and until R becomes infinite, electric Coulombian force will be there. Okay? So, what this electric field will do, theoretically speaking, it will send this test charge to infinity distance. The point at infinite distance I have taken as point B, which is the final position of the charge, where it has been thrown out of the electric field, correct? And why it is thrown out? Because electric field has got some capacity of doing work, it has got some potential at this very point, which we have to find out. Fine. But if we just release that test charge, what will happen? It will be accelerated. So, there will be increase in the kinetic energy also. We do not want to have any increase in kinetic energy, correct? And for that, we should allow the charge to move under equilibrium, correct? On the straight path, we should allow it to move with constant speed. If you want that, the charge should move under equilibrium, then when electric force is exerted this way, you also must continuously exert external force on this test charge in a direction opposite to electric force with the same magnitude. Then, during the displacement of this test charge from here to here, constantly it is acted upon by two oppositely directed forces of equal magnitudes. So resultant force would be 0, and then acceleration will be 0, and then it can move with constant velocity. Then it is said to be moving under equilibrium. Fine. Now in this case, electric force is exerted this way. I am showing it by symbol vector F. Displacement along x-axis is also undergone in the same direction, shown by symbol vector dx. Correct? Let us find out amount of work done by electric force as the test charge moves from A to B. As you have studied in 11th standard, it can be found out from line integration of electric force. Line integration of electric force. Line integration of electric force over the path of motion from initial position to final position. Simple. Come on, WAB equals to integration of vector F dot vector dx from A to B. Same integration I have written here, but what do you mean by vector F dot vector dx? It is F into dx into cos theta. But what is theta at that time? Angle between electric force and displacement vectors. Come on, because these two vectors are pointing in the same direction, angle between them must be 0 degree. Correct? Now cos 0 degree is 1, dx as it is. This is magnitude of Coulombian force. It is k into product of magnitudes of two charges divided by square of the distance between them. It is mathematically k q q0 upon x square. Now because k q q0 is constant, can be taken out of the symbol of integration. Then left is integration from A to B, 1 upon x square dx, 1 upon x square dx. Correct? Now same term I have written here, but integration 1 upon x square dx is nothing but minus 1 upon x. Correct? And now because the variable is in terms of distance, I should specify the limits also in terms of distance. Don't write these 2 points, write the distances of those points from the source charge. Distance of point A from source charge is r. So in place of A, I am writing small r as the lower limit. Come on, in place of B, write distance of point B from the source charge, which is infinite. So in place of B, I am writing infinity as upper limit. Okay, fine. Don't put the points right now, put their distances from the source charge. And now you know how to put the limits. Just check here also. Because point B is at infinite distance, instead of B I am putting now infinity. W from A to infinity is this much. You know how to put the limits. K q q0 as it is. Come on, minus 1 upon x. In place of x, I should write first of all upper limit, that is infinity. After putting minus sign, in this term I am supposed to write, come on, lower limit in place of x. That is in place of x I should write r. So right here minus 1 upon r, minus 1 upon r. Simplify, minus 1 upon infinity. 1 upon infinity is 0. Minus minus plus. So k q q0 upon r. K q q0 upon r. And now just bring this q0 in the denominator. Correct? On the left side. So w from A to infinity divided by q0 will be kq upon r, kq upon r. Tell me, what is this? Amount of work done by electric force exerted on a unit positive charge while shifting it under equilibrium from a given point to infinity is called electric potential of given electric field at a given point. Given point is right now point A. That's why this will give you electric potential at point A, which is shown by symbol VA. Correct? This right hand side is as it is. Now instead of Q, I just write in general, suppose Q dash. Okay? Just make a mere change in the symbol. Come on, instead of Q I am putting Q dash. Okay, fine. How would you define electric potential from this point of view? Here given electric field is repulsive. Okay, so better you include that also in the definition. Amount of work done by electric force exerted on a unit positive charge while shifting it under equilibrium from a given point in the given repulsive electric field to infinity is called electric potential of that repulsive electric field at that very point. Fine. Now we go for attractive electric field. Attractive electric field. Look here. Electric potential of attractive electric field at a given point. Because electric field is right now attractive, you must think of source charge which should be negative. So this is a negative source charge, and because it is a negative charge, its electric field is pointing towards it. Here electric field lines are radially inward, radially inward. Here radially outward, here radially inward. Here you can say centrifugal. Centrifugal means away from center, and here centripetal towards the center. Fine. That source charge is Q dash, which at present is minus Q. Q dash equals to minus Q. Now here what we do? We think of a test charge Q0 shown by symbol green dot at this initial position, which is considered right now at infinity. So distance of this point from this source charge I am taking infinite. Fine. This is the initial position, so initial distance is x1. What we do now, we just release this test charge. As soon as you release it, what this attractive electric field will do? Will attract this positive charge, because test charge is the positive charge. When source charge is negative, test charge is positive, naturally this will attract this, correct? So it will provide attractive electric force in this direction. Fine. Then displacement also is undergone in the same direction. Fine. And now let it come to point B, correct? But now tell me, if you release this charge, then it will move under the influence of this electric force. Then again it will be accelerated. If it is getting accelerated, its kinetic energy will increase. But we don't want that, correct? We want that charge should move under equilibrium with constant velocity, correct? Then for that sake, what it should do, when this test charge is moving on this straight path, at that time, you should constantly provide an external force in a direction opposite to direction of electric force with the same magnitude. Then during the entire displacement of that test charge, the resultant force exerted on the test charge would be 0. When resultant force is 0, acceleration will be 0, velocity of the charge will be constant. It is said to be moving under equilibrium, correct? Fine. Now by the time it comes from A to B, what is the amount of work done on that test charge by this attractive electric field? Let us find out. According to formula WAB, work done is given by line integration of force, correct? Right now this force is electric force. Come on, initial position is point A, final position is point B. Simple. This integration as it is, vector f dot vector dx means f into dx into cos theta. What is theta right now? Angle between electric force and displacement. Angle between electric force and displacement will be 0 because both the vectors are right now pointing in the same direction. Fine. Now cos 0 is 1, dx as it is, magnitude of electric force given by Coulomb's law. It is k into product of magnitudes of two charges divided by square of the distance between them. K q0 upon x square, correct? Because k q0 is constant, you can take it out of the symbol of integration. That's what I have done here. Left is integration 1 upon x square dx. Integration 1 upon x square dx. Now, because point A is taken at infinite distance, instead of point A, now I am putting infinity. Instead of point A, put infinity, B point as it is. This k cube q0 as it is, integration 1 upon x square dx. Everybody must remember now. Come on, it is minus 1 upon x. And now don't put the points, you put their distances from the source charge. Distance of point A from this source charge is infinity. So in place of A, I am writing infinity as a lower limit. And what is the distance of point B from this source charge? It is r. So in place of B, I am putting small r as the upper limit. Now put up the limits. This left side as it is, Come on, k q q0 as it is, put up the limits, minus 1 upon x. Instead of x, I am supposed to write the upper limit. Right now it is small r. After putting minus sign, in place of x, I should write infinity in this bracketed term. Minus 1 upon infinity. Minus 1 upon infinity. Correct? Come on, minus minus plus. 1 upon infinity will be 0. Now it is minus k q q0 upon r. Minus k q q0 upon r. Come on, transfer this q0 here. So w from infinity to point B upon q0. That equals to k into minus q upon r. K into minus q upon r. Correct? Tell me, what is this? Amount of work done. Amount of work done by electric force exerted on a unit of positive charge while shifting it under equilibrium from infinity to a given point in the given attractive electric field is called electric potential of that attractive electric field at that very point. Right now given point is point B, so I am putting the symbol VB. Correct? I repeat, whenever you see any ratio, denominator you should take 1 unit. Okay? Come on, define this electric potential of attractive electric field at a given point from this ratio. Look, amount of work done by electric force exerted on a unit positive charge while shifting it under equilibrium from infinity to a given point in the given attractive electric field is called electric potential of that attractive electric field at that very point. Last time, amount of work done by electric force exerted on unit positive charge while shifting it under equilibrium from infinity to a given point in the given attractive electric field is called electric potential of that attractive electric field at that very point. Right now that point is point B, so I am putting symbol VB. Correct? Now this right hand side as it is, but tell me, in place of minus q, can you write q dash? Yes, we can write. So in place of minus q, I am putting q dash. So here also we got k into q dash upon r. Here also k into q dash upon r. Why don't you speak in words? K into source charge divided by distance of a point of observation from source charge. K into source charge divided by distance of point of observation from source charge. Got it? Fine. In general, we have suppose point P in the given electric field, then the potential symbol you may write Vp at point P. Come on, it is K into source charge divided by distance of point of observation from source charge. It is K into Q dash upon R. But mind well, Q dash is source charge. It may be positive, may be negative. So I am writing here Q dash equals to plus or minus Q. Q dash equals to plus or minus Q. Correct? Tell me, is there any confusion? Frankly speaking, you please tell me. Is there any confusion? I hope your all doubts, your all confusions are removed now. We have adopted same policy in both the derivations. We have found out the work done by electric force. And because electric field has got capacity of doing some work, then only we say it can have potential energy, then only it can have electric potential at various points. Correct? So just keeping this point in mind, we have derived the formula of electric potential produced by a point charge. Correct? I hope you must have understood everything and you will appreciate this labor which I have put in. Thank you.